Okay, welcome back. Now that we've essentially solved the inverse problem between a charge distribution and some samples in electric scalar potential, it's tempting to basically cross your arms and put up your feet and wipe your hands, I guess, and consider the problem solved. But the practical reality is that it's not really as simple as that. There's a lot of complications that emerge when you're trying to do inverse problems that don't exactly work with the forward problem. So this is going to introduce the idea of what's called a well-posed problem versus an ill-posed problem. And so to demonstrate an ill-posed problem, I'd like you to just consider this little situation here. Okay, so we have 2-point charges, which we'll just call Q1 and Q2. Actually, I've got that backwards. This is Q1 over here, and this is Q2. And we have up here, there's a sample phi1 here and a sample phi2. So what I would like to do is calculate Q1 and Q2 given phi1 and phi2 here. So just for the sake of argument, let's suppose I told you that this is 1 volt here and this is also 1 volt over here. Okay, given that information, is it possible to rederive the magnitudes of these two charges? And the answer is not really. And so watch what happens here. So you notice I've given the positions of the sources here. So this is 1 meter over and to the right, and this is 1 meter to the left. This is also 1 meter down, 1 meter up. So given that information, what is the distance, say, from here to here and here to here? So we'll say R11, R12, and of course there's R22 here, and then there's an R21 over here. So we'll write that out as R11 is equal to, so the distance here, we have a right triangle, and it's just the square root of 2 meters, which incidentally, because of the symmetry, is the same as all of these other distances. So I'm going to write R12 equals R21 equals R22. Now immediately, this should trigger some alarm bells, because when we actually write out the system of equations here, you notice we'll get something that looks like the following. So my system matrix, I'll have basically 1 over root 2 times 1, 1, 1, 1. Then we'll have a Q1, Q2. So every value here is 1 over root 2 for 1 over that, equals 4 pi epsilon naught V1, or 1 volt here, 4 pi epsilon naught V2, like so. This is a very bad thing in linear algebra. And the reason is because this matrix here has no inverse. That is, it cannot be inverted. A matrix like that, which cannot be inverted, is often said to be singular. But in the more broad sense of this problem, we have what is called an ill-posed problem. That is, there is no unique solution for these charges that will satisfy these given values of scalar potential. So this, you can obviously, if you think about it, there's some intuition as to why that would be the case. So for example, you look at this situation here and imagine drawing a line like so. And due to the symmetry of this problem, all of the samples, all the information up here has to perfectly mirror on the bottom over here, because there's really no difference. So that means if I give you some information about a sample up here, to then repeat that information down here is essentially told you nothing new about this system. So for all practical purposes, it's as if I only gave you one piece of information and then repeated it twice. So the same information repeated twice isn't actually 2 pieces of information, it's just the same one piece of information. So as a result, you have a scenario where essentially there is no unique solution here. There are infinitely many possible combinations of Q1 and Q2 that can give rise to these two values of scalar potential. So any problem like that has no unique solution is said to be ill-posed, like so. The only way to get around from this is this second sample here, this observation sample, has to be moved somewhere different from that sample up there. So, for example, if instead of having it here, what if I just kind of moved it off to the left like this? Now, what will happen essentially is this matrix will change here. Say, so if this were 1 meter like so, and this is 2 meters here, then this distance from here to here would be the square root of 1 plus 4, or 5. So now what happens is I get a 1 and a 1, say, for this distance up here, but then I will get something like 1 over square root of 5 here. So we'll write this like so, 1 over root 2, 1 over root 2, then I will have from 1, 2, this will be 1 over root 5, and this will just be 1, like so. So now I have a matrix that can, in principle, be inverted, and there is now, again, a unique solution for Q1 and Q2. In this situation, you would have what is called a well-posed problem, meaning that there is now a unique solution.